Now let's think about how we're going to represent longitudinal waves. So let's first talk a little bit more about what a longitudinal wave is so we can think about how we want to represent it. We said that it's a case where the motion is actually going to be in the same direction, the motion of the particles that make up the medium is in the same direction as the motion of the wave itself. So you can think about this as the individual particles going back and forth, and that allows our pulse to travel. So this is equilibrium, means that our particles would be equally spaced. And these particles could be, for instance, coils in our spring, our slinky, or these could be, for instance, particles in air if we're thinking about sound. So the initial condition of our wave is that we have this compressed area here. At later times, this compression has actually moved to the side. So we see that we still have a pulse that is traveling, but now it's a pulse of compression. You can see for this scenario that some of our particles stay in the exact same spot, right? These first two, for instance, don't move. This third one moves over, but then moves back, and then stays in the same spot. The next one moves over, moves back a little more. And if we watch the ones before the pulse, initially it's actually stationary, but then it moves, and then it moves even more. So notice that these are actually moving back and forth. Keep in mind that we actually have time going this direction. So really, if I was to just trace out what's happening here, we have motion to the right, then we have motion back, and then motion back again. So all of our motion is happening in one direction in these plots, but we're using the second direction to represent time. So what can we actually plot here? We can actually plot these changes in position from our original equilibrium position. So what that's going to look like is delta x now is going to be this way, right? So this is going to be our x direction. And so not only do we have the x direction that is our horizontal axis, but we are also looking at how individual particles have moved in the x direction, and that will be on our vertical axis. So this is a lot trickier. Our vertical axis and our horizontal axis actually show the same direction, but they're showing different quantities. This is the position you're at, and this is the displacement at that position. So that's where it's helpful to try to analyze a picture like this first. Now again, keep in mind that this picture here was showing different times, and if we have a snapshot graph, this is only at one time. So this here is at time equals 0 seconds. So for us, that's going to be this one. And notice that here we show initially a positive displacement, which is true because this has gone positive, and then we have a bigger positive, smaller positive, and notice this is 0. This one has delta x equals 0, and if we look up here, it crosses the axis there. Now we have negative, and here we see negative, 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 0 back there. So we're always looking in the same direction, both for the position we're at and the displacement, but again, then our pulse would be traveling in time, which has been shown by these additional pictures here. So longitudinal waves can be a little bit tricky to represent and to think about, but once you have this plot here where you're looking at displacement versus position, we really get to analyze it the same way we do with transverse waves. But make sure when you're labeling your vertical direction that you're labeling it with the right type of displacement, whether it's longitudinal or transverse. So again, the vertical axis here is the displacement, in this case in delta x. It doesn't actually look like the wave, right? The wave itself in this case is not a string going up and down. The wave itself is actually some particles that are closer or farther apart from one another. Now another option, which we'll talk about with sound, is actually doing pressure. So here we're plotting the displacement. Has an individual particle moved to the right or to the left? Another option is actually just plotting how dense the particles are, which corresponds to pressure. So we'll get to that later when we talk about sound, which is the case that we would want to do that for.